All right, hi, I want to do a quick, or as quick as I can, but there's kind of a lot in this video about the intro to astronomy notes for this week so that you can get a 10 out of 10 for the graded assignment on Friday. So we start with the Earth's movements in relation to the sun. And so the first thing that we go over even this year, it's kind of a review, is the rotation. So the one thing that Earth does in space is rotates, right? It rotates counterclockwise around its own axis. So if you remember from latitude and longitude, the rotation of the Earth is going to be once a day, right? So one rotation is 360 degrees, one day is 24 hours, and if you go down into hours, it's going to be 15 degrees per hour. And in latitude and longitude, that's why we learned each time zone across the world is 15 degrees apart. So it's a different hour every 15 degrees apart if you're traveling. The second thing Earth does is it revolves, and we call this a revolution. A revolution is around the sun. So a rotation is around Earth's axis itself. A revolution is going around the sun. The Earth does this in about what we would say 365 days. And a revolution is about 360 degrees. So when we round it, we say that it approximately takes about 1 degree per day to revolve around the whole entire sun. All right, and we'll notice that this revolution path, right, is not a perfect circle. This is what we would call an ellipse. So an ellipse is a path or an orbit that a planet takes that is not perfectly circular. If it's not perfectly circular, it has an equation that you can figure out how not circular it is, called the eccentricity equation from page 1 of your reference tables. The eccentricity equation is the distance between foci. The foci is going to be, for anything in our solar system, one point would be the center of the sun, and another point is just outside of the sun. It's another point in space, right? So I can kind of just put that on here and I can make it up. So this would be the foci, these two. So what you would do is you would take the distance of this, and I'm making all this up, and I would say, I don't know, maybe it's 10 centimeters, right? Then you would need the length of the major axis, which is when the planet is the absolute furthest away from each other on both sides. So that would be one side is here, second side is there. So you would take this and you would find the distance of that, and I guess let's say this is 100 centimeters, and I'm making all this up because in class you would be using a ruler. So the eccentricity formula, right? The eccentricity formula is distance between foci, which is our 10, divided by our length of our major axis, which was 100 centimeters. And you would get 0.1. So our eccentricity that I just made up in this particular situation was 0.1. And this is a weird calculation because there is no unit. It's just 0.1. The eccentricity is 0.1. It's not centimeters per centimeters, et cetera, et cetera. It's just 0.1. The eccentricity is 0.1. So if your eccentricity is equal to 0, you're going to have a perfect circle. If your eccentricity is 1, you have a perfect straight line. So when it is closer to the number 1, you have a very ovally looking ellipse. So that's close to 1, to like the literal number 1. And then if you have a eccentricity that's closer to 0, like imagine you have like 0.002, that's really close to 0, then it would be more like a perfect circle that I probably can't really draw that well. That's my attempt at a perfect circle. All right, so close to 1, it's more like an oval. Close to 2, it's more like a perfect circle. All right, so let's see, that is the movements, rotation, 15 degrees per hour revolution, 1 degree per day around the sun. Eccentricity is the distance between foci over the length of the major axis. Close to 1 is a more elliptical, is what you would say. Close to 0 is less elliptical. Then what do we have? We have seasons and we have tilt. All right, so I'm going to also add gravity to this. Gravity. The way gravity works, if you are large and you are close, there is a high amount of gravity. If you are small and you are far away, there is a low amount of gravity. So I have positions 1 and 2. So everything is the same size, right? The sun is one size, the earth on both sides is the same size. Here, we have more gravity because it's closer. The closer something is, the closer two planets are to each other, the more gravity they have in between them. And then the bigger the planets are, the more gravity they have in between them. So the most exaggerated version is large planets in a close distance. The opposite of that would be small planets in a far distance. So in position 2, because they're further away, there's going to be less gravity in this area. And this kind of works like a slingshot too. When there's more gravity, Earth is able to move faster because it's giving the force of gravity is higher, so it has more energy, so it can move faster. So in this part at number 1, we're actually moving faster. And at number 2, we're moving slower in our revolution around the sun. All right, and then we have seasons, right? Last thing I have to go over is seasons. And don't forget, I'm doing this as kind of like a review of the notes, so hopefully just putting some better images or explanations to the notes. So seasons, we have our basic 1 and 2 position. These are like the perfect opposites. And actually, I'm going to make this 3, so it makes more sense later. So I'm going to have this 1, I'm going to have this as 3. Earlier I said that this was closer to the sun, right? And then we also said it's more gravity, because gravity, the closer and the bigger you are, the more gravity. Position 3 that I have here is further. And so the most average idea is, oh, we're really close to the sun, right? At position 1, that must be the summer, but that's not the case. This is actually the winter. This is actually where we are soon. We're going to be here soon. We'll be here June 21st. We were already here December 21st. So the reason why we are able to be closer to the sun in the winter but still be colder is because of the tilt of Earth. The tilt of Earth. Our axis is tilted at 23.5 degrees. So that means that we're not always facing, we're not always pointed towards the sun. Sometimes we're pointed away from the sun. So if I was going to draw in a 23.5 degree tilt at winter on my number 1 position, it would be like this, right? So the northern hemisphere is pointed away from the sun's rays, making it cold. There's lower insolation, lower incoming solar radiation, or lower angle of insolation, so it's colder, right? When I go here, my tilt stays the same way when I go over to summer. So now my northern hemisphere is pointed towards the sun, and the angle of insolation is higher. So we're further from the sun right now, but because we're pointed or tilted towards the sun, we have our summer. And we'll be tilted towards the sun the most maximum amount, June 21st, the summer solstice. Then we have two even positions. That's why I wanted to do this. So this would be like 2, and then this would be like 4. At position 2 and at position 4, in orientation with the sun, the tilt has no effect. It looks like straight up and down. It doesn't change. It's just the way that the Earth is revolving around the actual sun. So if I go this way to 2, I go from winter, then I go to spring. We call these the spring equinoxes. They call them equinoxes like equal because there's 12 hours of night and 12 hours of day. And then at 4, right, spring, summer, then I would go to fall, and it is the same type of position towards the sun, and it's the fall or the autumn or the fall equinox, etc. And these have similar temperatures because they're both tilted the same exact way towards the sun. All right, so that was the quickest review I can do of intro to astronomy.